Bonjour à tous. So this presentation is going to be in English. Thanks everyone for being here. Thanks to the organizers for having me. My name is Giulia Bianchi. I'm a senior data scientist at CybelAngel. At CybelAngel, we scan the non-indexed internet looking for data leaks. Every day we find billions of documents that are freely accessible online. Among these documents, there's a very few amount of them that is sensitive and that is important for our customers. So we deliver them to them through a SaaS interface. In order to identify the sensitivity of documents and the level of severity of the documents leaked, there's a team of analysts that analyze the documents and decides about their sensitivity and severity, and makes a report. So we have at the beginning billions of documents, and at the end a very few of qualified alerts. In order to enable the work and not to overload them with too many noisy documents, there is a pre-processing steps that allows to reduce the volume by filtering out non-interesting documents. This presentation is about the machine learning challenges that we face when we want to decrease this volume of alerts. Just to give you an idea and some numbers, this is about one precise use case that we have, and it's the volume regarding only 5 days last July. The machine learning model discarded automatically around 50,000 alerts, which means that the analysts received 5,000 alerts. They went through them. They detected 50 alerts that were investigated further, and only 10 of them were actually sent to our customers in the end. So one of the main challenges that we face with my team is that the sensitive alerts are very rare among all these documents, and the machine learning model has a hard time detecting them. Okay, so first of all, we treat the problem as a binary classification problem in which classes are very unbalanced. As an idea, in our training data, we have around 0.5% of positive examples. To understand why this is a challenge, I'm going to start by picturing out the balanced case. So when we have balanced classes, the positive and the negative classes are equally represented. So there's half of them. Now let's imagine the model predictions are the following one on the right-hand side. You can see that the model makes only 2 mistakes. So there's a non-sensitive document that is classified as sensitive, and the sensitive document that is classified as non-sensitive. So the corresponding performances, just taking into account the errors, the accuracy score, it's pretty high, it's 0.8, the accuracy score being the number of correctly classified documents over the total number of documents. So from this point of view, it's very good. Now, if we picture the unbalanced example, keeping the same numbers, so here you can see that the positive class is not as represented as the negative one. So if the model prediction, in the model prediction there are only 2 mistakes again, so one non-sensitive document classified as sensitive and one sensitive document classified as non-sensitive, we have again only 2 errors, so the accuracy score is the same, but you can clearly see that the second model, it's just useless. So how we can tackle the problem of to well classify these rare documents these are the ones that we are interested in. You can act at 4 steps during the machine learning pipeline, during data preparation, model training, model evaluation, or at final prediction. And the hypothesis that I make here is that we have enough data of good quality that are representative of reality. We know them, we did the exploration, and the feature engineering is okay. Now, this is because this is not specific to unbalanced classification. This is what you have to do in whatever machine learning problem. And here I just wanted to go a bit further. So the first option is about restoring class balance. Then during model training, we can act on the class weight. At model evaluation, we can use a more appropriate metric that captures better the actual performance of the model. And at final prediction, we can try to tweak the probability threshold. We are going through all of the 4 steps. Okay, so first one. Restoring the class balance is about making the positive class more represented in the dataset from a proportion point of view. So there are 2 ways. Either we add sensitive documents, or we remove non-sensitive documents. In the first case, we speak about oversampling. In the second one, about undersampling. First, so oversampling. The problem in the first place is that we don't have enough sensitive documents. So how do we make up some of them to increase their representation? There's an easy way to just duplicate some of them and use them in training more than once. This is easy, but there's a high risk of overfitting because the model risks to learn by heart on this data, and when it has production data, it doesn't know what to do anymore. And the second option is to make up just new data, starting from the one that are already in the dataset. It's a technique that is called SMOTE. It's based on the features of sensitive documents that exist in the dataset and makes up some new sensitive documents. It can improve the performances of the model during training. On the other hand, what I'm not sure about is that the model sees at training data that we'll never see at production. So maybe the performances will be a bit too optimistic, and when the model has to predict on production data, it won't really have enough information to actually distinguish and detect them. Undersampling, on the other hand, this is something that is really easier. We have a lot of non-sensitive documents in the dataset, so it's easy to just remove some of them randomly or with some criteria in mind. But there's a risk of potential loss of information, but it's less risky than oversampling. For our use case in CybelAngel, we used this undersampling. So I told you we had like 0.5% of positive class, and after undersampling, we got to 10%, around 10% of positive class. The second option is to act during model training and increase the minority class weight. The idea is to change the cost function that is optimized during training in order to give more importance on the errors that are made on the positive class. So if this is the log loss function in logistic regression, the first one, then you update it with 2 weights, W0 and W1. W0 is the weight for the negative class, so the non-sensitive documents, and W1 is the weight for the sensitive documents, for the positive class. If you choose W1 greater than W0, then the positive examples will have more weight during the training, during the optimization of the function. In scikit-learn, most of the models have a parameter that is called class weight that you can set. One value that you can use to start with is the opposite, is the inverse of the frequencies of the class. And also, we used these modified cost functions in our use cases. The first option is to act during model evaluation and choose a better metric. One metric that is usually used for binary classification is the ROC curve. A ROC curve has a false positive rate on the x-axis and true positive rate on the y-axis. The perfect model will be the one that has a ROC curve that goes through the top left of the plot of the ROC curve. It corresponds to a false positive rate of 0 and a true positive rate of 1. So if we want to ideally tend there, if you look at the formula, you will see that you will need to maximize true positives and true negatives, and to minimize false negatives and false positives. Now with unbalanced classes, true negative is naturally high because we have a lot of negative examples in the dataset, and the false positive is naturally small because we have a few positive examples in the dataset. So, the metric will be a little bit biased, and we'll see how. I'm taking back the examples that we previously saw. So with balanced classes first. These are the predictions that the model would have made with the two errors. So a false positive and a false negative. The accuracy score is again 0.8. This doesn't change. And tells us that the model is good. The false positive rate, we want it to be close to 0, and it's 0.2, so it's good again. And the true positive rate, we want it to be closer to 1, and here it's 0.88, so we are okay. All the metrics tells us that the model is good. If we switch to the unbalanced class scenario, the accuracy score, again 0.8, tells us that the model is good. False positive rate, 0.11, tells us that the model is good. But the true positive rate is 0. We want it to be 1. And here we have the first signal that the model is not performing well. A second metric that it's also very used is the precision recall curve. It is similar to the ROC curve, but we have the recall on the x-axis and the precision on the y-axis. Here the perfect classifier is the one that has a curve that goes towards the top right corner. And in this point, you will have a precision of 1 and the recall of 1. Now, in the two formula here, we don't have the true negatives anymore that biased the formula before. And if you want to tend to the perfect classifier point, we will need to maximize the true positive and minimize false positive and false negatives. Everything else that we said before is still true, but if we replace the example again, for the balanced scenario, all the metrics tells us that the model is good. It was good already before, and it's still good. In the unbalanced scenario, now we have two metrics that tells us that the model is not performing well. So these metrics are capturing better the actual performance of the model. Now here it's just an example, so visually you straight away understand that the model was not good. You didn't need the metrics to establish it. But when you have a lot of data, then it's much harder to state by just looking. Now the fourth option is to act at final prediction by tweaking the threshold. This is true for scikit-learn models, but it's also true for other frameworks. A trained model, it's an object that has two methods, predict_proba and predict. Predict_proba outputs a score that varies between 0 and 1. According to the model, it can represent actually a probability, and if the model is well calibrated, then it represents the proportion of positive samples in the dataset. Method model predict. Method predict outputs a label, so the actual class, and this is what we are interested in. At the end of the day, there's a document that arrives, and we want to know if it is sensitive or not sensitive. The score is less of an information for our analysts. By default, this label is set to 1 if the score is greater than 0.5, and is set to 0 if the score is less than 0.5. A threshold of 0.5 is good if the proportion of positive class in the dataset is 50%, but with the unbalanced class, this is not the case. So this is probably not the best choice of threshold. And this is where it becomes interesting, because the question is how to choose this threshold. And this is where you need to think a little bit more. According to the thresholds, all the metrics, all the quantities that we discussed before varies. True positive, true negatives, false positive and false negatives will change. And what you can do first, from a quantitative point of view, is to just choose the threshold that maximizes a quantity like the area under the curve. You choose it, and then you just have your threshold. And this cannot be enough because what you need to do is actually to think at what it means to choose a threshold and to have this number of false positive or this number of false negatives. And what is a good way to do from the qualitative point of view is to try to assign a business meaning to all these metrics. Now, just to contextualize this into what we do at CybelAngel, what does it mean to choose a threshold or another? For example, I can make a more conservative choice. And before that, imagine what happens at CybelAngel. So we have our analysts, and we give them a feed of alerts. They have on their computer a list of alerts, and they just go through them and decide which one is sensitive and which one is not. If I choose a higher recall and a lower precision, it means that they will have kind of a great number of alerts in their feed, and I am pretty sure, though, that among all of these documents, there are all the true leaks. So this is why it's a conservative choice. But as a consequence, if the feed is too big, then it will take much more time to the analyst to go through it, scan it, and there's possibly a delay into treating the feed, and our customers don't receive the alert early enough. So maybe the solution is that we need to employ another analyst. If we make, on the other hand, a less conservative choice, so we say, okay, let's reduce the volume at maximum, this could be good, could have a great impact on the fact that the analysts that are already there will be able to go through them. But we risk of missing out some of the true leaks. So if we miss out on leaks, then maybe our customers are not happy enough and they will just leave. So there is a a point in the middle to find, to choose the best threshold. And telling you that maybe we need one more analyst, or maybe we will lose money. This is the kind of business reasonment that we can attach to the metrics to be able to make a choice that is more data-driven. Okay, so that's almost the end. And what I would like you to go home with is that always spend time on the due diligence, always know your data, explore them, and it's always a time that is gained for later anyway. With unbalanced classes, performances may be too optimistic, so pay attention to that, and to overfit. This is also something that you pay attention for other machine learning problems, but especially here. All the techniques that I told you about, you can also try to be creative, combine them, and do what works for you. And always attach business meaning to what you're doing to make sure that that your model will have a meaning. Then enjoy the ride, of course, and thank you. Maybe there's time for questions, maybe not. There's time for questions. Let's see. I will be able to answer later if you want. No problem. Ah, une question.
Thanks for the presentation. It was very good.
Tu peux en français aussi si tu veux.
Je me demandais si dans les choix de modélisation, vous avez fait la différence entre des faux positifs et des faux négatifs, sachant qu'un faux négatif, c'est quand même plus grave dans votre cas.
Ouais, on a, en fait, on monitor les résultats et on regarde bien le false negative rate. So we send the feed to. On envoie les alertes aux analystes et parmi toutes celles qu'on a enlevées, on repioche 5% au hasard et on les envoie. Et comme ça, on voit si eux, ils vont envoyer quelques-unes parmi celles-ci. Et comme ça, on peut monitorer les false negatives.
D'accord. Mais dans la validation croisée du modèle, par exemple, est-ce qu'on peut prendre en compte plus facilement, plus fortement les faux négatifs par rapport aux faux positifs?
Alors on l'a pris vraiment en compte plus comme métrique quand on fait des évaluations sur precision recall, etc. On prend en compte celle-là, mais c'est pas forcément dans l'entraînement que ça pèse plus.
Ok.
Merci beaucoup.